Okay, we'll continue with identifying points of inflection and discussing concavity of the function. We'll start with number 27 here. And I think that what we're seeing here are just a lot of different algebraic techniques that we'll need to be able to apply these tools effectively across all types of functions. So hopefully you're getting something from that. We have x times x plus 3 to the 1/2 power. And we'll need to do a product rule here for the first derivative. F prime of x is 1. d2 will be 1/2 x plus 3 to the negative 1/2 times 1. So 1 d2 plus 2, which will be x plus 3 to the 1/2 d1, which is 1. Simplifying, we get x over 2 times x plus 3 to the negative 1/2 plus x plus 3 to the positive 1/2, and we'll factor out the least common multiple, x plus 3 to the negative 1/2, and that will leave. Hopefully you're getting the picture that when we do this, the other one will always come out as 1. So we'll get x over 2 plus x plus 3 to the first power. Multiply two numbers with the same base. We add exponents, so negative 1/2 plus 1 gives us positive 1/2. One more round of simplifying to the negative 1/2, and we get x over 2 plus x, so a half of an x plus a whole x is 3/2 x plus 3. Alright, we'll need the second derivative of this now. We may only be able to fit one of these on this page here. So let's start up here at the top. Second derivative would be, we'll use a product rule, 1 d2. So x plus 3 to the negative 1/2 power times 3/2. Alright, so we have 1 d2 plus 2, which would be 3x over 2 plus 3 times the derivative of the first, which will be negative 1/2 x plus 3 to the negative 3/2 times the derivative of the inside, which is just 1. So let's see what we get here. We now have 3/2 times x plus 3 to the negative 1/2. Then we have plus, let's see, we're going to have 1 and minus, we'll make that, we'll bring out the negative 1/2, and we have 3x over 2 plus 3 times x plus 3 to the negative 3/2. Alright, we want to factor out the least common, and so that'll always be the smallest one. Negative 3/2 is the smallest, x plus 3 to the negative 3/2. So we'll factor that out, x plus 3 to the negative 3/2. Then we'll have 3/2 x plus 3. Again, multiply two numbers with the same base. Negative 3/2 plus what equals negative 1/2? It's just 1 to the first power. So we factor that out. Then we get minus 1/2 times 3x over 2 plus 3. So work on simplifying the inside here. X plus 3 to the negative 3 halves. And multiplying all this out, we get 3x over 2 plus 9 over 2 minus 3x over 4 minus 3 over 2. Again, x plus 3, negative 3 halves. And 3x over 2 minus 3x over 4 is really 6x over 4 minus 3x over 4. So that's just 3x over 4. 9 halves minus 3 halves is 6 halves, so that's plus 3. And I think we're pretty close to being there. We have 3x over 4 plus 3 divided by x plus 3 to the negative 3. Well, now it's not to the negative, to the 3 halves. And if we multiply top and bottom by 4, it might be a little bit neater. We'll have 3x plus 12 over 4 times x plus 3 to the 3 halves, and one more, factor out the 3 times x plus 4 over 4 times x plus 3 to the 3 halves, and that is our second derivative. So much algebra going on in there, so many places to make mistakes, but hopefully we'll check and see if we got that all correct there. Alright, so a rational function is 0 when its numerator is 0. So we have x equals negative 4 as a potential point of inflection, and a rational function is undefined when its denominator is 0. We can see that x equals negative 3, that the derivative, the second derivative, is undefined. However, when we go back to our function here, we have square root of x plus 3. At negative 3 it's 0. That's true, but negative 3 is going to be an endpoint, and so we do not need to consider that. We can't go any further than negative. Well, can negative, very interesting here. So let's talk about the domain of this function, x times square root of x plus 3. The domain has got to be x values greater than or equal to negative 3. 27. Let's not put 27. So this function has a domain that is that x values have to be greater than or equal to negative 3. And if that's the case, then and for all values of x greater than negative 3, then we plug them into our, we can pick any value greater than negative 3, we can plug in x equals 0, and you'll see that our second derivative will always be positive. So that would lead me to believe then that both of these are really invalid as points of inflection. And f of x is concave up for all x in its domain. Now we'll bring in the graphing calculator and see if that's actually true. So we'll see what happens here. And we'll plug in x times square root of x plus 3 and zoom standard and see what we get. Well, in fact, we do have a graph that is concave up for all x. Let's take a snapshot of this. And we'll put that on the workspace. So hopefully you can see from this there are so many things to consider. We have to think about domain, and even though we found two places, 2 points, -3 and -4, that were valid points of inflection, one because the second derivative was 0 there, and the other because the second derivative was undefined there. Even though we found those, they really are not valid or are not meaningful to this particular function, because the graph to begin with has to have only values greater than or equal to -3, and -3 is at the end point, so we're really not going to be interested in end points as points of inflection because the concavity cannot change at an end point. So here we have x equals 3, and we can see based on our analysis that the graph was or is concave up for all values of x to the right of x equals not 3 but -3. Again, so much work involved in this. If you really want to understand math, you want to understand algebra, you want to understand calculus, you have to be able to do, or you have to do problems like this and struggle your way through them. Alright, we'll go on to number 29 in the next video since we don't have any room for that here.